So let's say we have a wire that's in a circle. Just a single wire. It's carrying current. Clockwise. Let's find the magnetic field in the plane of the circle, smack dab in the center. Number one, what direction will it be in, smack dab in the center?
I'm going to guess it's actually 0.
It will not be 0.
Well,
Good guess.
well, because there's parts that are going that way and parts that are going this way.
But you have to use your right hand the whole...
Well, no, I'm going the opposite direction.
Oh, gotcha.
So,
Shouldn't it be going into the board?
Yes. So when you put your thumb in the direction of the current, my fingers on the left-hand side of this piece of the wire into the board. As I keep following the wire around,
oh,
my fingers are still into the board.
okay.
I can't keep going. So due to this whole wire, the magnetic field will be into the board.
All in a row.
Right.
I need that. I don't know.
No worries. Okay. So, we need to pick a piece of the wire. DS is in the direction that the current flows, so at any one location it's going to be tangent to the circle. I'm going to just call it DS. R in the denominator, so I'm back using this equation here. R is the distance from the piece of wire to the point we're interested in. So it happens to be equal to the radius of this circle. R hat points from the piece of wire towards the point we're interested in. So since DS is tangent to the circle and R hat points towards the middle of the circle, they're already perpendicular. And they will be for any piece we look at. As we work our way around this loop, will R be changing?
No.
That's fabulous. R stays constant. So our equation, just magnitude-wise, since we've already found the direction, mu naught I over 4 pi. Remember, ds cross r hat is simply the magnitude of ds times the magnitude of r hat times the sine of the angle between them. But the angle between them is 90, sine of 90 is 1. So we simply get ds. R hat it just has a length of 1. Nifty thing is, all of that's a constant, so we simply have the integral ds. But we need limits.
0 to 2 pi.
0 to 2 pi r. Yeah, so it needs to be a length. ds as represents a length. So 0 to 2 pi r. So we have all this stuff. Integral of ds is s, plugging in our limits, 2 pi r. So 2 pi simplifies that down to a 2. The r cancels one of those. So we get mu naught I over 2r is the magnitude of our field. What do you think it would do if we had, say, 2 or 3 loops?
Screen force change.
Increase how much current's flowing around. Simply need to multiply by however many loops we have. Now that's limited. You can't have too many loops. The loops have to be more or less the same distance away. So it can't be tall and it can't be too wide. So this equation will work for a few loops. If you have, say, 2, 4, 5, so forth. What do you think would be different, say, had half a loop. So single wire bends through a semicircle and keeps going. These straight portions are creating magnetic fields. But what does the magnetic field look like around a straight wire? Makes nice little circles around it, right? Will a circle drawn around this wire pass through that point? No. These long straight segments will not produce a magnetic field at that specific point. It's along the line of the wire. The magnetic field makes circles around the wire, so you have to go laterally away from the straight wire in order to see the magnetic field due to it. So these straight portions are not producing fields here. So only this hemispherical or semicircle portion is.
Since it's half a circle, it's half the value. Like this 4.
Exactly. Now we can write this as a generic equation. If we want. Our integral would have been the same, but we would have integrated to just pi r instead of 2 pi r. Generically, we could integrate to some generic r times theta, where theta is the number of radians that curve moves through. So we would get mu naught I over the 4 pi r squared times r theta. R's will cancel, or one of them will. Mu naught I over 4 pi r times theta will work for any curved segment. You have to keep in mind theta needs to be in radians.
And provided, does the dot have to be
In the center.
in the center
In the
of
center
that
of the curve.
circular arc?
Correct.
So,
Yes.
oh, but wouldn't that make, okay, so say we have a 45-degree arc,
Uh-huh.
and we had to have our dot considerably lower than the other two wire, or not, I'm
Well,
not thinking,
The point would be, it would work out, it would be that.
what about something like that?
You'd have to integrate.
Okay.
So if you had a point down here somewhere from this wire, you would have to re-integrate. You'd have to start here again. Because even the straight portions will contribute at this point.
Now we know we're fine.
No, I'm not going to ask you to do that.
The only way I can think to do that is piecewise.
Because that'd probably be the easiest way. Break it into pieces and do it.
Unit steps.
Yeah.
If
There are a couple other magnetic fields that your book has derived. For example, it's derived one for the circular loop, but out here on its axis further away. I can't remember which other ones they've done. But just check them out. Make sure you know what they're used for. But all of these equations are the magnetic fields created by the wire that's carrying current. So it's its own magnetic field. If you have multiple wires, you simply find their individual magnetic fields and you can add them up. Turns out if you have multiple wires and they're all carrying current, they can actually interact with each other. They can exert forces on each other, depending upon how their magnetic fields meet up.